Hello, welcome to everyone in this video. This is our lecture number 6. Already 5 lectures cover of this mathematical method for semester 3. Okay. In the first lecture we discuss about the singular point of the differential equation. Then second and third lecture actually we discuss about the Frobenius method. And fourth lecture we discuss about the legendary polynomial, legendary differential equation, legendary polynomial, generating function, recurrence relation, and orthogonal property of the legendary polynomial. In the last lecture, that is lecture 5, we discuss all about the Bessel's differential equation, is generating function, recurrence relation, orthogonal property, etc. We discuss in the previous last lecture number 5. So if you want to watch the previous lecture, you can go through the description box, link are given there. In this lecture, lecture number 6, we want to discuss that is the Hermite differential equation, Hermite polynomial, generating function, recurrence relation, orthogonal property of the Hermite polynomial. Okay, so I think you understand all the roots of those lectures previous, and that's one. So let's start. You can go through the syllabus of the mathematical methods, mathematical physics part 2, which is for syllabus semester 3 of BSc physics honors under University of Calcutta. In the first lecture we covered this portion, and the second and third we lecture covered this one, and fourth lecture and the fifth lectures covered the rest of the parts except the Hermite polynomial, the Hermite differential equation, and this the multiple expansion of electrostatics, and this one. These three portion actually escaped. We all cover up to lecture number 5. In this lecture we covered the Hermite differential equation, and in the next lecture, that is lecture number 7, we will be discuss about these two things, that is multiple expansion of electrostatics and the arrest disks or the Fraunhofer diffraction through the circular aperture. These two will be discussed in terms of this Frobenius method or differential equation, right? So let's start with the Hermite differential equation. This is all the syllabus. Hermite differential equation. You can see this is the Hermite differential equation, that is d2y dx square minus 2x dy dx plus 2 lambda y. This can be any constant. You can take n, no problem. Okay. So if you attend the first lecture, you know how to find out the singular point, that's the regular singular point or irregular singular point or ordinary point. So using this concept, you can easily find out this ordinary point or regular singular point or irregular singular point. You can see this is the p of x and this is the q of x. So at x equal to 0, p of x and qx's both are finite. That's why x equal to 0 is a ordinary point. Clear? Next, at x equal to infinity, p of x infinity, but x into p of x finite, but this is also infinite, so this will be the irregular or non-essential singular point. I think clear about x equal to infinity. This is a not regular, this is irregular singular point because this is the infinite, this will be the diverge. That's why. So x equal to 0 is ordinary point, x equal to infinity is irregular singular point. You know the Frobenius method is applicable for ordinary point and regular singular point. So x equal to 0, which is ordinary point, can be applicable for the to solve the Frobenius method of this differential equation. That's why we take this solution. You know the method of the Frobenius method. In lecture 2 and 3 we discuss about the Frobenius method. So in this method we just take first y equal to this summation k equal to 0 to infinity a k x to the power m plus k, where a0 not equal to 0. The higher power must be not equals to 0. Coefficient of highest power, initial power must not does not equals to 0. So it's take derivative with respect to x, and the double derivative will be like that. So put this value in this differential equation, Hermite differential equation, put these two expression, you will be get these things. And now if we compare the coefficient and rearranging them, now the coefficient of x to the power m minus 2, here we can get x to the power m minus 2 if we put k equals to 0, right? But here we did not get x to the power m minus 2, because if to get the x to the power m minus 2 you need to put k equals to minus 2, which is not possible because k start from 0. Same thing here also. That's why if x to the power m minus 2 will be arises from this one, where put the value k equals to 0. So this is a0, this is m, and this is m minus 1. So m equals to 0, m equals to 1, because a0 not equal to 0. Now if you compare, that is the coefficient x to the power m minus 1, you can see here the x to the power m minus 1 also arises from this term only if you put k equals to 1. Here we did not get any x to the power m minus 1 or any x to the power m minus 1. This also because you need to put k equal to minus 1, which is not possible. So x to the power m minus 1 arises from the first summation, which is a1 m plus 1 m equals to 0, where we get m equal to 0 or m equals to minus 1 or a1 equal to 0. In case of coefficient of x to the power m plus k, you can see this will be the arises. X to the power m plus k means you need to put here k equal to k plus 2, such that you get x to the power m plus k. Okay, so k equals to k plus 2. So this will be the concept. So from where will we get the recurrence relation for this Hermite differential equation. Now put this value m equals to 0, because we get the m equals to 0 and the m equals to 1. If we put this value m equals to 0, a0 not equal to 0, a1 not equal to 0, because if you take m equals to 0, this if you take m equals to 0, so a1 not the must did not be 0, either 0 or not, no problem, but at m equals to 0, we can take a1 not equal to 0, no problem. Okay, sorry. So when m equals to 0, the recurrence relation will become like that. So for even value of k, put a k equal to 0 in this relation, you will be get the relation between a0 and a2 and a0. Then if you put the value at k equal to 2, you will be get the relation between a4 and a2, and put this value of a2 in terms of a0, you will be get the k2 value in terms of a0. Similarly k4, that is a4 in terms of a6, k equal to 4, that is a6, which is in terms of a0, and so on. We can find out the coefficient, right? And the for odd coefficient, put this value, odd value of k, that is k equals to 1, you will be get this relation using this the recurrence relation, right? So a3 related with a1, a5 related with a1, and so on. So the total solution will be break into these two, m equals to 0. So this will be the even part and this is the odd part. The summation will be like that. So this is the total solution of this harmonic differential equation for m equals to 0. Now if you take m equals to 1, then you can see here m equals to 1, a1 not equal to 0, that's no problem. But here there is no option for m equals to 1, so a1 must be 0. Clear? So at m equals to 1, a0 not equal to 0, but a1 must be 0. That's mean the odd coefficient must be 0, because a1 0 means a3 0 means a5 0 means a7 0, and so on. So the odd coefficient must be 0, the only even coefficient are present, and the recurrence relation become like that. Put k equals to 0, you will be get a2 in terms of a0, a4 in terms of a0, a6 in terms of a0. If you put this value of m, which is 1, will be get this relation. You can see this is the not the other solution, that is not the new solution, because this portion already discussed, this portion already obtained in the previous solution, and you can see this is the same things like here. Okay, so the total solution will be like that. This is the total solution. Finally the total solution will be like that of the differential equation. Clear? I think clear all about this solution of the differential equation, Hermite differential equation. Next, go to the Hermite polynomial. For finding the Hermite polynomial, you need to put the coefficient value a0, which is like that. From where, putting this value, from where you can get the Hermite polynomial, that is the Hermite polynomial expression in terms of infinite series, where n equals to n by 2 when n is even, and this is when n is odd. This will be the after rearranging them, you can easily write down this Hermite polynomial in case of n equals to even and n equals to odd. This is for n equals to even. Actually 2n is even. This is for even, right? This is for even coefficient, and this is for odd coefficient. You can see here this is 2n plus 1, so this is odd. This is 2n, this is 2n plus 1. Clear? So this for even, this will be the expression, and for odd, this will be the expression. You can see you can find out the value of h0x, h1x, h2x. Just put this value. H0x means using this equation, h1x means using this equation, h2x means this equation. Just using this equation, you can find out h0x 1, h1x is 2x, h2x is 4x square minus 2. Now, yeah, if you wants to find out this polynomial, Hermite polynomial, these are actually Hermite polynomials. Hermite polynomials, right? Polynomials. the Hermite polynomials will be like that. These are the expression you can see here, and the corresponding graph will be like that, that h0x which is constant like that, h1x which is slope like that, h2x is parabolic, h3x is green color, h4x is blue color like that. Okay, I think clear about this expression, how we can find this expression. This expression also find by this Rodriguez formula. Rodriguez formula, in case of the legendary polynomial, we also use a Rodriguez formula. Here we also use the Rodriguez formula for the Hermite polynomial, which is given is like that: h and x equal to minus 1 whole to the power n e to the power x square del d n dx to the power n e to the power minus x square. Put n equal to 0, you can easily find out. Put n equals to 0 in this expression, you will be get 1. Put n equals to 1, h1x, which is find out like that. Put n equals to 2, you will be get h2x. This is not h3, this is the h2x. This is the h2x. Clear? So h2x equal to 4x square minus 2, and this one. I think clear. Now comes into the generating function. In the previous two lecture we discussed the generating function for legendary polynomial and Bessel polynomial, or Bessel differential equation, and in that harmonic polynomial also use this generating function. Actually this generating function get the same things as we obtain the solution in this Frobenius method. This function actually very helpful for our calculation, that's why we take this generating function. So this generating function for Hermite polynomial will be like that: it is 2xt minus t square. In case of legendary polynomial, we take xy. You can take xt, no problem. So in that case, we take in the Bessel formula we also take xt, but in the legendary polynomial we take xy. In this generating function we take xy. You can take this xt. So this is the generating function of Hermite polynomial. If you expand this exponential e to the power x, you know the infinite series expansion of e to the power x equal to this. So if you expand this expression, this is not ended, this is plus minus, sorry, this is plus dot dot dot. So if we compare this coefficient to the power 0, you can see there is to the power 0 is 1, and here to the power 0 is 1 by 0 factorial, which is 1. So h0x is 1. If we compare the coefficient to the power 1, you can see here 2x is the coefficient of to the power 1. Here 1 by 1 factorial h1x. So h1x equal to 2x. If we compare the t to the power 2, that is t to the power 2 will arises minus 1, and here this square. So this two term arises for t square, and this is the h2x by 2 factorial. So h2 equal to like that. T cube arises from, if you take this product term and the cube term here. So if you compare these two term, h3 will be like that. So using generating function, you also get the Hermite polynomial. Using Lorentz formula, you can also get h1 h2 h3, and from this definition of Hermite polynomial also you get then h1 h0 h1 h2 h3. Okay, which is favorable, you can find out this Hermite polynomial. Okay, so after getting Hermite polynomial, you can easily find out some recurrence relation for Hermite polynomial. First one is this 2n hn minus 1x h prime nx, right? So the no, you know this generating function. If you derivative with respect to x, because this prime denoted this derivative with respect to x, right? So if you take this derivative with respect to x, you'll be get this one, and this is nothing but the summation of that one. Put this value, and if you compare t to the power n, t to the power n will be like that, because this is t, so this will be t plus 1, so you need to put n minus 1. That's why put here n minus 1, and t to the power n means you put n equals to n, so you will be get this relation. I think clear about this recurrence relation. Next one will be like that: 2x hn(x) equal to 2n hn minus 1x plus hn plus 1x. So this is the generating function. If you derivative with respect to t, the previous one was with respect to x, and this one is the with respect to t. If you derivative with respect to t of this expression, you will be get this one equal to that one with respect to t derivative. Because there is no prime, that means this derivation will be not with respect to x. That's why we take derivative with respect to t, because the n is in front of s. So if you derivative this thing, this n form will be arises here. So then product these two things because this is nothing but the summation of this one. So put this one and product these two things, and then coefficient of t to the power n. You can see here, put n equals to n here, but here you need to put n equals to n minus 1 to get the t to the power n, and here we need to put n equals to n plus 1 to get the t to the power n, right? So I think here I put a mistake. This is n plus 1. Put n equals to n plus 1 to get t to the power n. So this is n plus 1, so this will be cancelled out. You will be get n factorial here. So this is the n factorial, and these two term are the similar thing. Now if you use this n factorial in product, so this is nothing but n factorial, and this is n minus 1 factorial, so you will be get 2 n. There is a n, because this is nothing but n into n minus 1 factorial. So n minus 1 n minus 1 cancel out, only n is arises remaining, n is remaining here. So you will be get this differential equation, sorry, this recurrence relation will be obtained. This is the number 2. Number 3, this is the number 3. From formula 1 you will be get this one, from formula 2 you will be get this 2, using formula 1 in formula 2, because this is h 2n, h n minus 1 x is h prime x, so put here, and this rearranging, this is very simple. Next, using this relation from the last formula 3, you will be get this one. Double prime means derivative with respect to x, that's why you derivative with respect to x again, and you will be get this is double derivative, this is 2 into this, that is derivative of x is 1, and derivative of this is 1, this, and derivative of this one. And from formula 1, you know this is the formula, so if you put n equals to n plus 1, you will be get these things, and use this formula here, use this formula in here, sorry, in that point, and rearranging them, you will be get this relation. Clear? I think you can do this relation by this process. Next is like that, you know this generating function. If you put at x equals to minus x replaced by minus x and t replaced by minus t, you can see here this is nothing but the same thing. So if you put this expression and then compare the coefficient of t to the power n, you can finally obtain this relation. Okay, so I think clear how we will be get the recurrence relation for Hermite polynomial. Next is the orthogonal property of Hermite polynomial. This is nothing but these are the two Hermite polynomial. Their product, integration of this product must be equals to 0 if m is not equals to n. Clear? So this is all about the Hermite differential equation, Hermite polynomial, recurrence relation, orthogonality, etc. This is all about me. This is my contact details, and this is my YouTube channel details. Go to this channel, you will get the different physics related video. Like this session if you learn something from this session. Share this video to your friends, either he or she also get benefit from this video. Subscribe this channel if you new in this channel, or those already subscribed, thanks for subscription. Press the bell icon to get the notification of upcoming video. So take care. In the next class we will be discuss in the rest part of this lecture. So take care, we'll meet in the next video as soon as possible. Thank you.